Okay, good afternoon, class. Today we'll be talking about um, temperature and heat, and this is a very interesting topic. As you know, we are in week 6, so if you look at your syllabus, um, we should be timely with our schedule. Again, we are in week 6, and we'll be discussing today about temperature and heat. Okay, so temperature and heat, of course, are referred um, to hotness and cold. We're talking about temperature and heat. Of course, we can allude to means that something is being hot or something is being cold. However, they're not the same. Okay, so the concept of temperature and heat play an important role in our everyday lives, as we know, right? Temperature, of course, tells us if something is hot or cold, right? This means the temperature is relative, okay? Um, or I should say, is a relative measure or indicative if something is either hot or cold. It may seem like I'm repeating myself, but I am saying different things. Okay. Of course, when you touch something, you can determine whether it's hot or it's cold. That's based on our relative indicator. Okay. But there's no way to be able to quantify how hot or how cold that item is. Right. So the way temperature is typically being measured is through a thermometer. Right. That's how we can quantitatively know that by some kind of standard, this is how hot or how cold an item is. Okay, so this instrument, of course, determines temperature very accurately. Keep in mind that all substances, of course, they expand as you increase the temperature, and they will contract as you decrease that temperature. Okay, so some of the most commonly used thermometers is a liquid and a gas thermometer. Okay, I think all of us typically we know that. So you have a liquid in a bulb, right? We're talking about this one down here. Okay. So there's a liquid in the bulb, and of course, as it senses any kind of heat, it begins to expand. And that's why you see the red readings typically rise in a thermometer. And you also have what you know as a digital ear thermometer, which typically uses infrared radiation to generate its heat to be able to increase or give you a measure of how hot that individual is. And they typically use that for more pediatric applications. Pretty much put it in your ear, which is what I have right here. Okay, so these are just different forms of how you can measure um, temperature. Of course, this is something that we normally put in our mouth, and this is an act where they can actually put it in our ear to also determine the temperature of the body. Okay. So knowing now we know how to measure um, temperature, what scales are being used as an indicator? Okay, so from a Fahrenheit scale, um, we see here that under ice conditions, okay, that's going to be 32 degrees Fahrenheit, which is nothing more than 0 degrees Fahrenheit. I mean 0 degrees Celsius. I'm sorry. And under boiling or steam conditions, it's going to be 212 degrees Fahrenheit. Okay, so the little formation of this little circle in F is nothing more than degree Fahrenheit. That's typically how it's being pronounced. Okay. Another temperature scale is our Celsius scale, and at cold or at ice conditions, it's going to have a 0 degree Celsius, and under steam conditions, and this is an E right here. I mean A right here. I'm sorry. Under steam conditions, it's going to be 100 degrees Celsius. Okay, so it's being pronounced degrees Celsius. Okay. Another temperature scale on the lower limit is what we call absolute zero, known as a Kelvin scale. Okay. This is a lot really used a lot of research atmospheric conditions as well. Well, we're dealing with vacuum. Okay. Um, However, there's a correlation between the Kelvin scale and the Celsius scale. And that correlation is, if you want to find the Kelvin and you're given your Celsius temperature, add 273 to it, and that will give you your Kelvin temperature. Now, the correlation between Fahrenheit and Celsius is itemized here, whereby the temperature of your Fahrenheit is nothing more than 9/5 times the temperature of your Celsius plus 32. Okay. Now, if you want to go the other way, whereby you want to be able to solve for the temperature of your Celsius, it will be 5/9 times the temperature of your Fahrenheit minus 32. Okay. So again, if you want to be able to find if you've been given the Celsius temperature and you've been asked to find or convert to Fahrenheit, this is the equation you typically would use: 9/5 times whatever that temperature is in Celsius plus 32. Conversely, if you were given the temperature in Fahrenheit and you're asked to find the temperature in degrees Celsius, you would use this equation right here. So let's look at an example whereby we have the normal human body, of course, is commonly taken to be 98.6 degrees Fahrenheit. And we want to be able to know what is that temperature in degrees Celsius. Okay, so like I said, going back to this equation right here, we've been given degree Fahrenheit, and we need to find out what is the actual temperature in degrees Celsius. Okay, so we're going to use that formula, TC, which stands for temperature in Celsius, equals 5/9 times the temperature in Fahrenheit that they gave us, which was 98.6 degrees Fahrenheit minus 32. And when you crunch the numbers, you're going to get 37 degrees Celsius. Okay. Now, another phenomenon, we just talked about temperature. Let's talk about heat. Okay. So heat is described as a form of energy, right? So it can be transferred from one object to the next. And you have different variations of this transfer mode. We have what's known as conduction, convection, and then radiation, which we'll talk about more as we go further into our discussion. So heat, as I said before, is nothing more than a transfer of energy between two objects that are at different temperatures. Okay, so if object 1 has a high temperature and it comes in contact with object 2, of course a lot of that transfer of heat is going to be transferred. A lot of that heat from object 1 will be transferred to object 2 that has a low temperature. Because again, these two items want to at least reach some kind of equilibrium. Okay. Now the units for heat, as I said, heat is a form of energy or transfer of energy. And we know the energy from our previous studies is joules. Okay. Now, common and traditional unit for measuring energy is calories as well. So 1 calorie is defined as the amount of heat it takes to raise 1 gram of pure water by 1 degree Celsius at atmospheric pressure. Okay. So that would be the definition of a calorie. Okay. Now, there's a correlation between calories and joules, whereby 1 calorie equals 4.186 joules. Okay. Keep in mind that 1 kilo is 1,000 grams. Okay. Or I put grams there, but I guess whenever you see, kg, it just means 1,000 grams. Okay. The K just means 1,000. Okay. So I just want you to be aware of this when you see it. And then 1 kilocal is just 1,000 calories. So one food calorie is equivalent to 1,000 calories. Is equivalent to 1 kilocal. One food calorie equals 4,186 joules, right? Which is equivalent to 4.2 kilojoules. Again, we have 4,186, and I can move the decimal place 1, 2, 3, so it makes it 4. I could times 4.2 times 10 to the third. But I have to account for this third, so I gotta put a K and let them know that it's kilojoules. Okay. Now, food calories indicate the amount of energy produced when a given amount of particular food is completely burned. Okay, because I know a lot of us are typically very health conscious, so the amount of calories that goes in, one has to ask himself, how much energy is it going to cost? Do I have to generate or produce to be able to burn the calories that I just consumed? Okay. So as I said before, joules is the SI unit of heat. Now British thermal unit, BTUs, will be the actual units for heat from an imperial standpoint. Air conditioning applications typically use a lot of BTUs. So I want you to ask yourself as you're driving, and especially when you drive on a bridge, ask yourself about the thermal expansion joints. What are they? What do they do? And how do they behave throughout the year in terms of the fluctuation of temperature? That would be a good exercise just to kind of quiz yourself. Okay. So move a little further into heat. We want to talk about specific heat and latent heat. So as we have already proven that while heat and temperature are quite different, right? They of course are related in some kind of ways. Right? When heat is added to a substance, the temperature generally increases, which is true. When it comes to materials, the internal makeup or the molecular structure are different. Therefore, the amount of heat energy that they may take to heat up aluminum may be different than silver. Okay. And again, put another way, these two materials respond differently to temperature. So how do we address that? So the difference is expressed in terms of the specific heat, right? The specific heat of a substance is the amount of heat necessary to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. And the unit for that is joules per kilogram per degree Celsius. And of course, it's also in kilocalories as well. So the greater the specific heat of a substance, the greater the amount of heat necessary to raise the temperature per unit mass. And think of that also how it applies to density as well. Okay. So materials that hold heat, we say has a very high heat capacity. The amount of heat needed to change the temperature of a given substance, right, can be outlined in this equation, whereby M is your mass, excuse me, C is your specific heat, and the delta T is your change in temperature. That is the amount of heat energy required, okay, to make a change within a substance. So for an example, they ask us how much heat in kilocal does it take to heat 80 kilograms of bath water from 12 degrees Celsius to 42 degrees Celsius. So essentially they're asking us how much heat is it going to require to raise the temperature of an object, in this case, which is water, which has a mass of 80 kilograms. Because that heat that is needed to raise the temperature of 80 kilograms is going to cost you and I money. Okay? So our equation would be MC times delta T, where the mass is 80 kilograms. Our C, the specific heat capacity, is 1 kilocal divided by kilograms per centigrade. And our delta T, which is the difference in temperature, will be 30 degrees Celsius. So we can multiply all this together, and we are going to get 2,400 kilocalories. So the latent heat, another related topic is latent heat. Excuse me. So phases of matter are classified, as you know, in our high school chemistry, as a solid. A matter can be classified as a solid, liquid, or gas. Okay? Now, when heat is added or taken away from any one of these phases, there will be a phase change. Okay? And that phase change is being characterized as latent heat. So you can see here in this schematic here that when this is on our x-axis, we have heat is added, right? And this is our temperature. So as our journey starts off as a linear line, meaning that we have an increase in heat, which equates an increase in temperature, we notice that under the solid phase, right, our temperature is constant, and then our heat added continues to increase. Then it gets to some point whereby now there's going to be an equivalence or a direct proportionality of the temperature that of the heat until it fully reaches its liquid state. All right. Now at that point in time, as heat is still being added to the system, the temperature now becomes constant. So as the liquid now evolves into like more of a gaseous state, you don't see a change in temperature until the liquid is fully converted into a gas. Now, in some cases, some instances, you'll find out that you can sublime a material, meaning you can go from a solid to a gaseous state. Okay, we call that sublimation. Likewise, if you want to change a phase from a gaseous state to a solid state, we call that deposition. Okay. Always keep in mind that heat required to change a solid into a liquid at the melting point can be noted as this equation right here, which is of course, H is the heat energy, right, needed to melt a substance. Okay, and the M is the mass, and the L sub F is nothing more than a latent heat of fusion. And for water, you'll see your table, but for water, here are the actual data. Similarly, at the boiling point, okay, this is the freezing point. At the boiling point, the amount of energy needed to change a mass of liquid to gas, okay, can be characterized as our latent heat of vaporization. Okay, so rather than using L sub F, we use L sub V. Okay. Now, looking at heat a little further, we talked about this a little briefly. How does heat transfer? Well, heat, as we said before, is a form of energy, right, in transit. Okay. And that medium that which it transfers can be conductive, can be can be in a convection form or in radiation. So here's a schematic just kind of addressing pictorially what do they mean by conduction. You have a medium here whereby that heat is coming in contact with this wood, but since there's a difference in temperature at this location, the temperature here, and the temperature there is quite different. This is going to be a lot cooler. This is going to be a lot hotter because it's in contact with this wood. So the temperature wants to travel from hot to cold. Likewise, for convection, we see how this is nothing more than the movement or the flow of molecules, right, from one destination to another, okay, through some mechanism of diffusion. And of course, radiation typically uses either visible light or ultraviolet light as a means of transferring energy. And there is a correlation between energy and wavelength of light, okay, which is a form of radiation, and this based on this, where h is your Planck's constant and nu is your frequency. Okay, E equals hc divided by lambda. C being the speed of light, lambda is the wavelength of light, and h is your Planck's constant. Okay. Now, when it comes to the different phases of matter, come here. We said that we have our phases could be either solid, liquid, or gas. And now, what distinguishes all of this is that when you look at their molecular structure, of course, in a solid, all the molecules are tightly bound, right? All the molecules are tightly bound. Now, when you begin to add heat to this, what happens now is the molecules begin not to be as tightly bound, changing its form from a solid to a liquid. And as you continue to increase the heat, it'll go pretty much from a liquid phase to a gaseous phase. And the reason why is because the bonds now have broken. These molecules have been liberated because the bonds have been broken. Okay? And you can see that here, where the molecules are free. Okay? So these molecules, based on the energy that they've been receiving from the heat, begin to impinge on the wall. Okay? And in doing so, you're creating some kind of pressure. And that pressure can be denoted as force divided by area. F equals force over A equals area. Conduction, as I said before, due to the medium, there's a temperature difference. Just kind of explain a little bit more here. Okay. How there's a molecular collision. Okay. Again, I have here the three forms of conduction. We have three forms of heat transfer. Okay. And I just typically explained again, dealing with radiation and what typically that means in terms of heat transfer. Now we can take it a step further and say that when volume and temperature are considered, right, our volume and temperature considered, and then our P and our N, we typically make that constant. We see it's going to be a direct proportionality. The volume is directly proportional to the temperature. Okay. 1 second here. I think I missed. Okay. Convection. Okay. Okay. So there's a direct correlation between volume and temperature. Okay. That's if we hold the pressure to be constant. Okay. And we also hold. What do we have here? And okay. Okay, the number of the molecules. Your N is your number of molecules. So Boyle's law typically addresses that the pressure is inversely proportional to the volume. Okay, and we have Gay-Lucas law. He typically says that the pressure is directly proportional to the temperature. Okay. Then we have what we know as an ideal situation, or I should say Charles' law. Before I go there, Charles' law tells us that that the volume, which is right here, I have that addressed right here. This is Charles' law right here. The volume is actually proportional to the temperature. Okay. Let me just erase this part here so we don't get confused. So this is Charles' law right here. Okay. Now in the case where the pressure and the number of molecules I said before, N, are considered, we have our volume and temperature are typically constant. We find out that the pressure is directly proportional to the number of molecules times the temperature, but inversely proportional to the volume. And we characterize this by ideal gas law. And it can be written as the pressure of P2 to P1 equals the ratio of V1 to V2 times the temperature of T2 to T1. And keep in mind that your temperature is always going to be in Kelvin. Okay. And how do we find Kelvin? If you're given Celsius, just add 273 to it, and then you'll get your Kelvin. 273 is nothing more than a constant conversion. Okay. So let's look at this example here, where it talks about the pressure increases in a rigid container. Right? And how does that happen? Well, a closed, rigid spray can holds, it's closed, and it holds a gas propellant that behaves like an ideal gas. The internal pressure is equivalent to 3 times normal atmospheric pressure at room temperature, which is 20 degrees Celsius. If the can is thrown in a fire that heats up to 100 degrees Celsius, what will be the internal pressure? Okay. So as we just think our way through this particular problem, right, we notice that as your temperature increases, right, there's going to be increase in the gas presence, right, the molecular movement of the gas. Therefore, there's going to be increase in pressure, because when the molecules begin to collide, they begin to collide against the container, and where it's being held, it's actually inducing pressure along the walls of the container. Okay? So we can say that the pressure now begins to increase as the temperature begins to increase. Okay? Now they told us that the volume, or the container, was closed. Container was closed, right? Therefore, no volume. There's no change in volume at all. Okay? So they told us we should consider ideal gas law, which is P2 over P1, right, equals, what was that equation here again? V1 over V2, V1 over V2 times T2 over T1. Well, they told us that the actual volume, the particular container was closed. It was a closed, rigid spray can. So this goes to 0. Okay. So we're left with P2 over P1 equals T2 over T1. Okay. Now, with that being said, I can say V1 equals V2. Okay. Now my P1, again, this is constant. My P1, they told me, is 3 times the normal atmospheric pressure. Okay. And atmospheric pressure is nothing more than 14.7, right, pounds per square inch, PSI. Okay. And then our temperature, T1, happens to be 20 degrees Celsius, which we want to be able to convert to Kelvin, which is going to be 20 degrees Celsius plus 273 equals 193 Kelvin. Okay. T2 was 100 degrees Celsius, and that's going to be 100 degrees Celsius plus 273 equals 373 Kelvin. Okay. Again, always convert your temperatures to Kelvin. So now, using our ideal gas law, P2 divided by P1 equals T2 divided by T1. Okay. And now we can solve for P2, which is going to be P1 times T2 divided by T1. Okay. So I'll let you do the math on this. We already know what the pressure is. We know what the temperature is, T2. And we also know what the temperature is for T1. Again, your answer should be in pounds per square inch. Pounds per square inch. Okay. Thank you very much. I hope this helps. Kindly let me know if you need any further assistance. I'll be here to help you. Please let me know how you like the video. Any kind of feedback would be definitely helpful. Thank you so much. I appreciate you. Thank you.